the Computational Linear Algebra class. We'll be looking today at Eigen things. We'll give you an introduction to them. We'll talk about this idea of fixed directions, which is where eigenvalues, one of the ways we can look at them. Talk about how to get eigenvalues and eigenvectors, a little bit more what they mean, we'll strive for generality. Look at a special case of the geometry associated with symmetric matrices. Look at quadratic forms and what happens when we have repeated maps. So first, to start with a sort of realistic example or physical example. This is a video you may have seen bits and pieces of. This is Tacoma Narrows Bridge, which in 1940 swayed violently during only 42-mile-an-hour winds, and this bridge later collapsed. And we're going to talk about this and see how some of this is related to eigenvalues and fixed directions and math that can be used to design safer and better bridges today. So a linear map is described by a matrix. It has some properties. When we've looked at things before, we've looked at how the phoenix gets mapped. We talked about this idea of the action ellipse and how things happen. And the stretching and rotating that goes on of a linear map is part of its important properties. And for linear maps, this can be captured by its eigen things, its eigenvalues, and its eigenvectors. I mean, we'll see how to capture all that in this lecture. So when we looked at the video of that bridge, from shortly before it's collapsed, you look at it and you can sort of see waves in it. And in today's world, we now know how to do careful eigenanalysis before any bridge is built, so we can put them together. So eigenvalues, eigenvectors play an important role in structural mechanics, but eigenvalues and eigenvectors in higher dimensions have lots of other applications. We'll talk about those later when we look at how we can apply them to things from face recognition to how does Google make billions of dollars, which depends on eigenvalues. So as you watch that bridge wiggle and collapse, you can see the wave form in it. And then finally those waves, of course, break the structure because there's just too much stress and strain on it and it falls apart. And of course we want to make sure we never do that again. Yet despite all the modern tools we've been using, there can still be problems. So here you see an example from a bridge built in Russia. And in 2010 you can see these same waves, and this is in like 20-mile-an-hour winds. If you look, you can see the road bending up and down, and this is just from the wind going over the bridge. Today we actually have a different solution because once they understand how it works. So inside of that bridge or the underneath that bridge look like that. They solve this problem by putting these weights in here, and they're sort of active dampening, and they can be used to change the eigenmodes of the bridge depending on the directions the winds go so that they can make it more stable. So what do we mean by eigenvalues? We're going to start by looking at what we call fixed directions. So we've already looked at maps, and if I have a uniform scaling in the E1 direction, then the direction is mapped to itself, and E2 axis can be mapped to itself. So if I do any scaling, regular scaling, I can scale it down or I can scale things up, then any vector CE1 or DE2 is mapped back to a multiple of itself. Okay. Now another case, which is not as simple, is if I just shear in the E1 direction. So I'm going to shear it this way. Now any vector in the E1 direction is just CE1. So if I take a vector up here at the top, it becomes some constant times E1, take some vector down here, but the E2 direction is not the same. And so in this map, in the shear map, the E1 direction is a fixed direction, right? Things just got mapped to a multiple of themselves, so it's not exactly fixed. The direction is fixed, the magnitude is not. But the E2 direction, things change significantly. So the idea of fixed directions these are directions that are not changed by the map. All vectors in the fixed direction change only in their length. And once you start looking at it that way, of course, we can now think of that in a matrix form, go back to our non-geometric, but to the algebraic form, and say, well, what we want to find the vectors R such that A times R is equal to lambda times R, right? That is, when I multiply this vector times the matrix, I just get some scaled value of that vector. And we're going to disregard the trivial solution of 0 because 0 is always true for that equation. Okay. So in 2D, we only have two directions because there's only two linearly independent directions. Everything else would be a combination of them. We're going to look for a special property we'll talk about later for symmetric matrices, which are these two directions will be orthogonal. And for non-symmetric matrices, they don't have to, they won't be no orthogonal, but they'll still be up to 2 directions. So why are they called eigenthings? Well, fixed directions are called eigenvectors, and they're get this name from when they were first written about, which come from the German word Eigen, meaning special or proper. So obviously, of all the directions associated with this matrix, the directions that map back to themselves are very special, since they are eigenvectors. And the factor that says how much is it scaled by, lambda here, is called its eigenvalues. And really, when we look at matrices, understanding eigenvalues and eigenvectors are a key to understanding the geometry of what that linear map does. So, how are we going to find the eigenvalues of a 2 by 2 matrix, actually, in a general matrix? Well, since we can just look at the algebra, we know that A times R is equal to lambda times R. That's what we started with. But we could also look at that as equal to lambda times the identity matrix times R, because multiplying by the identity matrix doesn't change anything. And now we can gather these up on the same side, and we can write that as the matrix A minus lambda times I times R. So this is now a matrix equals 0. And so we have a matrix equation. The matrix A minus lambda I maps the non-zero vector R to the 0 vector. Okay, now what does that tell us? Well, it tells us that since it's going to map it to the 0 vector, it's the homogeneous solution problem we talked about before. That means it has to be ranked efficient. In particular, that means that the determinant of A minus lambda I is equal to 0. And in this case, because we've written lambda in this equation, we're going to say that we're going to call this thing the characteristic polynomial. And it's called the characteristic polynomial even in higher dimensions as well. And whenever this A minus lambda I is equal to 0, then we have an eigenvalue, and we can get its associated eigenvector. Okay, so how do we actually represent that? Well, let's take a numeric example, makes it a little easier. So let's think of a matrix we've already seen, 2, 1, 1, 2. Right? That matrix scales the circle into this ellipse. We're going to calculate its characteristic polynomial by literally just putting in minus lambda on the diagonal and then computing its determinant. So we stick in minus lambda, compute the determinant. Again, we do the determinant with a cross, so we get lambda squared, and collect all the terms. We're going to get lambda squared minus 4 lambda plus 3. That's just a bit of algebra. And this polynomial has 2 real roots. Lambda 1 equals 3, and lambda 2 equals 1. And you can verify or check that any one of those, you can just stick that back in. You put in 3, you get 9 minus 12 plus 3 is 0, and it's just equal 1. And for 2D, finding the real roots finding the roots are easy, because you can just remember that for any quadratic equation, a lambda squared plus b lambda plus c, you have the solution minus b plus or minus the square root of b squared minus 4ac divided by 2a. So you can remember that formula. In general, what I really need you to know is that it is this characteristic polynomial, and that's how you get to it, and then you want to find the roots of the polynomial. So when we go to find the roots of that, another way of looking at that is to remember that we're going to write this, the quadratic equation is going to be lambda minus lambda 1 times lambda minus lambda 2 equals 0. And that's going to give us, because for a thing, now lambda 1 and lambda 2 may be the same. By convention, we're going to let lambda 1 be the larger in absolute value or magnitude of those 2 values. So we're going to call lambda 1 the dominant eigenvalue. And once we look at it this way, the determinant of A minus lambda I, we know it's going to have this form. We also then know that there's a special thing, that is that if I put in 0, the determinant of A is going to be lambda 1 times lambda 2. Right? So this brings back together the idea of the determinants and eigenvalues. And so the determinant measures the change in the unit area of the square mapped to the parallel, as it was mapped to the parallelogram. So the determinant tells us how much the change is happening. Eigenvalues indicate the scaling of certain fixed directions defined by A. Okay. And so when, for example, before we had the determinant going to 0 because the matrix was degenerate, then one of these two directions, one of the two fixed directions is going to go away. So let's go back and try another example. If I want to find R1 and R2 corresponding to those two eigenvalues, now I want to get the eigenvectors. How am I going to do that? Well, again, I can just sort of plug these in. If I take lambda 1, so I get 3, I know that a minus lambda I times r is equal to 0, so I'm going to take lambda, stick it in, and that tells me that minus 1, 1, 1 minus 1 times r equals 0. So now we have a homogeneous system and a rank 1 matrix. This has infinitely many solutions. So if I go to this and I try and do some forward elimination, I'm just going to get, if I go and shear this to make it go away, I get that minus 1, 1, 0, 0 equals r1 is equal to 0. So that basically says I can assign what I want to r2, 1, and then I can stick that back in because I have infinitely many solutions. And I'm going to get that r1 is equal to c times 1, 1. And this is actually why there's infinitely many solutions. For any value of c, this is going to be true. And again, we can just verify that. We can go back in, stick c11 into this equation, and you'll see you'll get minus 1, 1, or minus c, and here we'll get c minus c, and they'll cancel out, and we'll get 0 for both of our answers. We can find the second eigenvector in a similar way. We basically just stick it back in. Run through the multiplication, solve for this, and again we have a degenerate case, and now because it's 1, 1, 1, 1, we're going to have to say that r2, our second eigenvector, is c times the vector minus 1, 1. And if we go back and recheck this, 1 minus 1 is not stretched, it's mapped to itself. Actually go all the way back to the figure here. If we look at this, we'll see that this vector, 1, 1, right, is the connection between the center and the third element of this tip up here. The third element of this tip up here, it didn't move. And if I look down here at 1 minus 1, this direction here, which is this particular thing, it's about 8 up from here, we'll see that that one didn't move. So our eigenvectors are the directions that did not move. They just scaled. They didn't go anywhere else. Where if I were to, for example, look at this direction up to this tip, or actually let's just go straight up to the beak, you'll notice the beak moved. It went to the right. Okay. But this direction here, right, over to the tip of his wing at 1, 1, 1 did not. Okay, so those gives us our two eigenvectors. Generally, people will normalize eigenvectors so that they have a unit magnitude, and this is just because obviously it's c times this value, and so any value of c will work. So how do I say what is an eigenvector in general? Well, we're going to normalize it so it has length 1. In this case, since both of these have length 2, we're going to multiply, or square root of 2. We're going to multiply by 1 over square root of 2, and now they'll both be unit vectors. So the dominant eigenvector is the eigenvector that's associated with the dominant eigenvalue. Just go back to this for a second. And what do you see about that dominant eigenvalue? In this case, it's the one that got larger. So it's the larger magnitude of the two. So these both got scaled along these directions and only scaled along those directions. And this one was scaled by 3, and this one was scaled by 1, and so that's the dominant eigenvector. Okay, just sort of go through a quick another example. I'm not going to go through all the math for this one, but if I start with a matrix 3, 0, 8, minus 1, I can go through, build a characteristic polynomial, and get my eigenvalues and eigenvectors. And for this one, I'm going to end up with an eigenvector. The dominant eigenvector is 1, 2, associated with the eigenvalue 3. And again, if you draw out this map, I'm not showing everything here. I'm just drawing this little line, but I want you to think about this. Maybe apply it in MATLAB to your circle to get a feel for what's going on. Right? This direction does not change. The direction 1, 2 does not change, and everything just follows through for our eigenvalues. And we'll come back and talk a little about this more when we talk about the idea of mapping, repeating maps. So as I apply something, but if I take the map 1, 0, 3, 0.3, 0.31, and I apply it, this also has eigenvalues along that line. And so the first mapping, the value of the eigendirection doesn't change, and the eigenvector direction here doesn't change, but things just get scaled up in those directions. And if I keep scaling up, those directions are going to keep scaling up. So I want to bring this back a little bit and relate it back to our the bridge we started with. So we think about the forces of a spring, right? There's forces, and I can apply force, and the spring eventually pushes back. And this is important because if I'm thinking about something like a physical structure like a bridge, even if I get a force going in it, the natural property of the material is going to make it want to come back. So here we see now a plate vibrating. You'll see these sort of points right along the edges. These are the points that really aren't moving. And that's just because as the wave goes through this, those are the nodal points of the wave. But what you can imagine now is as the wind is blowing over this road, there's an eigenvector, or the bridge has an eigenvector, which is a direction where if you push it, it just doesn't move, and in other directions it scales up and down. And so now as the wind was going over this bridge, it continued like this spring to push in some directions, and it continued to amplify it. Other directions, so if the wind were to come along this way, along the length of this, it might not actually generate much force at all, because in that direction, the direction of the force and the direction of the map associated with the stiffness of the bridge aren't aligned. But when you happen to push it in the direction of its eigenvectors, then the bridge begins to oscillate like this plate here is doing. And the wind continues to build those oscillations, which is what led to the kind of waves that we saw in those bridges. Wind in some direction, in the eigenvector direction, continues to build the amplitude of what's going on in the bridge. So that led to the problem we saw on the bridge. So now we want to talk about this and look in more general. We had a couple of examples. Things are a lot more complicated, and they'll become more choices as we go to high dimensions. But when we solve for this eigenvector and eigenvalues, we started by building the characteristic polynomial, and so we then found where it was at 0. Excuse me. So if we look at a quadratic polynomial, right, which is what we had some, lambda squared something, lambda 1. A quadratic polynomial can actually be one of three cases. It either has no eigenvalue or no zeros, exactly 1 zero, or 2 real zeros. So in terms of real zeros, the eigenvalues, we can either have none, 1, or 2. So if there are no real zeros, then A has no fixed directions. Okay, so if you think about it, every rotation is a map that has this. A rotation map maps every vector. Nothing is unchanged. So if I rotate, every vector has to move. If we look at its characteristic equation, so we know this is a rotation vector, we're just going to stick in the minus lambdas on the diagonal. So we're going to get minus lambda 1, minus 1, minus lambda. Take its characteristic polynomial, we're going to get the polynomial that looks like lambda squared plus 1 equals 0. But this has no real solutions. In fact, so by looking at this, we can say, oh look, this map does not have any real solutions. It has no real solutions. That means it has no fixed directions. Everything has to move. Okay. So what is this second case where we have just 1? Well, here's an example. 1, 1/2, 0, 1. We already saw the example that if I just shear in the E1 direction, the E1 direction is maintained and no other direction is. Let's just go ahead and verify that. We put in 1 minus lambda on the diagonal, compute the characteristic polynomial. We get 1 minus lambda squared equals 0. So lambda 1 equals lambda 2 equals 1. There is one direction. Now, how do we get that? Well, we're going to go back in. We're going to put in lambda equals 1 on our diagonal, and we're going to try and find the eigenvectors. So we're going to get 0, 1/2, 0, 0. We have to column pivot to be able to solve this. And then we'll see that the vector, if we set R1 equals 1, then R, the overall vector, will be equal to C times 1, 0. The last column just disappears. Sorry about that cut off there. So again, we just sort of plug back in lambda, get a homogeneous equation. Generally have to do some pitting because it's homogeneous. There's going to be some zeros someplace, and then solve that to get our eigenvector. But there's another special case. If one of the eigenvalues is 0, for example, the projection matrix, if A is equal to 0.5, 0.5, 0.5, 0.5, then the characteristic equation looks like lambda times lambda minus 1 equals 0. Just stuck it in, run through the algebra, which tells us that lambda 1 equals 1 and lambda 2 equals 0. So if we go to do this and we look at the second eigenvector for this, we're going to find out that we put in 0.5, 0.5 R2 equals 0, 0, because we just put it minus lambda or minus 0 down the diagonal, so it didn't change anything. We got to do, again, Gaussian forward elimination. We're going to get 0.5, 0.5, 0, 0 equals R2, and R2 is equal to C times minus 1, 1. Okay, so this map multiplies R2 to the 0 vector. Okay, have we seen a direction? What's the direction that's going to go to the 0 vector in these before? So the map reduces the dimensionality down to rank 1, and the eigenvector associated with the 0 eigenvalue is in the kernel or the null space. Here it is the kernel, but in higher dimensions, the eigenvector associated with any 0 eigenvalue is in the kernel space or the null space. So when we get eigenvalues, and some of them are 0, it tells us a lot about these are the directions where the map doesn't do anything. But again, if we think about what this was, right, this was a projection, and that meant we went down to one line. So the direction that's in the direction of the line is the first eigenvector, and it's going to be maintained. And the other direction, the direction we're going to throw away, is what we're going to end up keeping here. So any matrix that is rank 1 is omnipotent. So a squared equals a. The one eigenvalue 0, we're going to let lambda be the other non-zero eigenvector. So what does that tell us? Well, we're going to sort of see that a times r is equal to lambda times r. We already know that. But a squared times r has got to be equal to lambda times a times r. We just multiply both sides by a. And that tells us that lambda r is equal to lambda squared r. That tells us that lambda is r. I'm sorry, lambda equals 1. So for any omnipotent matrix, we're going to have a lambda equals 1. So in fact, that allows us to see that any 2D projection matrix always has eigenvalues 0 and 1 because a 2D projection matrix is omnipotent. Once I've projected things onto the line, I keep projecting them on the line. Nothing else happens. So as a general statement, a 2 by 2 matrix with one 0 eigenvalue always has rank 1. The number of non-zero eigenvalues is going to be the same as the rank. So now let's look at some other special cases. These come up a lot, and so even though we're going to leave just looking at them as matrices for a second, we'll see a lot of other values as we start applying these to problems, and that's where the linear algebra ties to the real world. So symmetric matrices often arise in practice. So if I'm going to look at a matrix where A is equal to A transpose, and we'll look at some examples in terms of quadratics and conics. And there's lots of examples in classical mechanics, elastic theory, quantum mechanics, thermodynamics, and even things in computer spaces where we're looking, for example, at distances. If I go there and come back, you can end up lots of things end up being symmetric. So real symmetric matrices have some nice advantages in terms of how to work with them. First of all, although we're not going to prove it, you can show that eigenvalues for real symmetric matrices are always real. It has all real values, not imaginary ones. It has interesting geometric interpretations. So the Eigen decomposition we're going to talk about next has some nice properties that makes it easy to understand. In fact, I'd like to think of everything in terms of the nearest symmetric matrix, and it helps me understand the geometry of stuff. And the structure allows for very stable and efficient algorithms. So lots of times we're going to want to work with things just because they're convenient to end. Okay, so now let's look at the little math behind these symmetric matrices. If I start with just the two eigenvector equations, we know AR1 is equal to lambda 1 R1, AR2 equals lambda 2 R2. That's true in general, nothing special about the matrix there. But since the matrix is symmetric, I also know that AR1 transpose is equal to lambda 1 R1 transpose. And now I can use the fact that the product of the transpose is the transpose of the products. I can work that through. And I'll get R1 transpose A equals lambda 1 R1 transpose. I can multiply both sides of these by R2. So I'm just going to put R2 on the right-hand side of both of these. And now if I go back up to this second equation, I can just pre-multiply it by R1 transpose, assuming that R1 and R2 are not both the zero vector. I'm going to get lambda 1 R1 transpose R2 is equal to lambda 2 R1 transpose R2. Right? Or combining those all together, since they have the same second part, I have lambda 1 minus lambda 2 times R1 transpose R2 equals 0. This just follows for any symmetric matrix that lambda 1 minus lambda 2 times R1 transpose R2 equals 0. Because we just use the symmetry property up there for the transpose. So if I go back in, and if I think about the case where lambda 1 is not equal to lambda 2, which is the more general case, then we'll get that R1 transpose times R2 is equal to 0. And what does that mean? Well, if the two eigenvectors are 0, that means they're orthogonal. Okay, now we can also look at this in a matrix form. I can take A times R1 equals lambda R1, A R2 equals lambda 2 R2. Right? Just combine them back into a matrix, define a new matrix R, which is the columns of the two eigenvectors. and a matrix capital lambda, which is just the eigenvalues on the diagonal. And I'll get that A times R, where R is the matrix of eigenvectors, is equal to R times the matrix of diagonal matrix of eigenvalues. So A times R for a numeric example. Here's 2, 1, 1, 2. Here's the eigenvectors as we normalize them: 1 over the square root of 2, 1 over the square root of 2, minus 1 over the square root of 2. And that's going to be equal to this. So we can also look at this as a way of decomposing the matrix. And since we're in the case we just drew, we did use normalized eigenvectors. If we assume that R1 transpose R is equal to 1, so the length of R1 and the length of R2 is 1, if both of those are true, then we already know they're orthogonal. And the two conditions, being orthogonal and having length 1, leads to a term we call orthonormal. Okay, so this tells us that for symmetric matrices, in general, the eigenvalues are orthonormal. They're length 1 and orthogonal. We can put all those in matrix form, so we can put R1 and R2 back into the matrix, and we say R transpose R equals the identity matrix, which means that it's R inverse is equal to R transpose. So R turns out to be orthogonal matrix. And if you're not seeing this, go back and remember, right? We said that R1 transpose R1 is 1, R1 transpose R2 is 1. That gives us the first piece, and they're orthogonal, which gives us the other two diagonals. So we get the main diagonals from these two and the off diagonals from those two, and that gives us that R transpose R equals 0. So the identity matrix. But since R transpose R is the identity matrix, that means it's its own inverse and it's an orthogonal matrix. In fact, these two properties in general mean it's an orthogonal matrix. Since we know now that we know what the inverse is, I can post multiply our previous equation, AR equals R lambda. I can post multiply that by R transpose, and I'll get that A is equal to R lambda R transpose, which is what we call the eigen decomposition of A. And basically, this says that the eigenvectors, those directions that where things are fixed, can transform into a diagonal matrix, where we can see this now as R inverse AR, and A is diagonalizable. So any symmetric matrix that comes out of this is diagonalizable. This idea of a matrix decomposition is a fundamental and useful tool in linear algebra. It gives insights to the action of the matrix, helps us understand what it's going to do, and it's also part of how we can build some very efficient methods for solving it. When we want to find the eigenvectors of really large dimensions, we don't even necessarily find all of them. We can just use this diagonalization property to find some of them. So we can look at this in terms of its geometry. If I just think of A as this map, right? A, this is the map 2, 1, 1, 2, right? It's going to produce this geometric output. Now we can think of it as 3 steps because of that decomposition. We can think of the first step, R, as rotate by minus 45 degrees, R transpose. Then we're going to think of it as, we're starting from the right-hand side. We're going to go R transpose lambda R. So R transpose is rotate by minus 45 degrees. So notice how the tips of this have rotated back. Then we're going to scale, but we're only scaling along the axes. So we're going to scale this axis by 3 and that axis by 1, and then rotate it back up. Okay, so this linear map preserves lengths and angles in terms of the rotations, right? And all we have to worry about is the diagonal matrix that's scaling the coordinate axes. So a general symmetric matrix, remember, this was true for any symmetric matrix. A general symmetric matrix is going to be something we can break down into a 3-stage process of rotate, scale along with the eigenvalues, scale along the axes, and then rotate it back. Every symmetric matrix has some directions that are going to be fixed, so we can rotate it so those fixed directions are the axes, scale along the axes, and then rotate it back so those fixed directions are the directions we want them to go. So in general, this gives us a very nice geometric interpretation of any matrix. And although we've been doing this here in 2D, all this is going to generalize. We look to higher dimensions. So this allows us to go back and look at the action of our map on a vector. So we have our map A on some vector x. we can look at this and take, of course, AX equals R lambda R transpose X. We can multiply that all out, just put it in, multiply out that, and we'll get that the matrix, we'll get lambda 1 R1 R1 transpose X plus lambda 2 R2 transpose X. And recall that this form is something you've seen before. R1 R1 transpose is just a projection onto RK. So another way of looking at the action of the map is it's going to project everything. X is going to get projected onto the first eigenvalue, a vector, scaled by the eigenvalue, plus some projection onto the second eigenvector times its eigenvalue. So the actions of A can be interpreted as a combination of projections onto the orthogonal eigenvectors. Again, this is for symmetric matrices. So when you look at this, you can just sort of say, oh, look, here are the eigenvectors. I'm going to do everything as a projection onto those. Put that into a numeric example. Going back to our 2, 1, 1, 2 example, if I take some value x equals 1/2, to our 2 1/2, we can look at what the two projection matrices are. R1 R1 transpose is all 1/2s. R2 transpose is minus 1/2, 1/2, minus 1/2, 1. Right? It gives us these two directions, R1 and R2, our projection. Okay, so the action of the map is then going to be 3 times this projection matrix on X plus P2, because there's just 1, on X. You can multiply that out and see that, yes, that actually gives you the same thing as multiplying A times X. Now you might be wondering, why would you ever want to take a matrix, blow it up into two matrices, and do the math twice? But this is really to help give you an intuition about what's going on, because there'll be other times when we want to use this property of it's a projection into these directions and not actually compute everything. This turns out to be especially true when we don't necessarily want to ever compute A. And then it turns out there'll be problems where we can compute the eigenvectors without computing everything and doing all the products all the time. So there's another set of special forms that come up. We call these quadratic forms. And these come up in lots of different applications where we end up with something where we have some constants times v1 squared plus something times v1 v2 and something times v2 squared, right? This is a quadratic form. And every quadratic form could be written as a 2 by 2 symmetric matrix where I'm going to take the the vector v1, v2, describing the two dimensions, and I can write it as v transpose cv. Okay, so this is algebraically the same as that. And now we can look at this in terms of its matrix form. And this can be thought of in a sort of higher dimensional setting. If I want to sort of see why we call them quadratic forms, I can also look at this by looking at the set of v1, v2, and f of v1, v2. And they actually form a quadratic surface, so things you've seen. So these give me things like paraboloids, ellipsoids, hyperboloids over the unit circle. And these tell us a lot about different shapes. Okay, so all of these come from quadratics. For each of these, we could actually take them and look at what is their corresponding matrices. So quadratics here, we are going to end up with 2, 0, 0.5, so it's 2 v1 squared plus 0.5 v squared. So you can sort of see how you're going to take anything you would have as a quadratic and write them down in terms of this matrix. You go back to V and fill them out. But now what's interesting is to relate these back to our eigenvalues and eigenvectors, which is why we're talking about them now, is that if I look at these, I can look at these and ask questions, what are their eigenvalues and eigenvectors? Well, because they have this nice diagonal form, you can just read off, right? Remember, these were defined by this matrix, V transpose CV. So we can just read off of that matrix C and get our eigenvalues. So the magnitude of C is 1, so lambda 1 is 2, and lambda 2 is 0.05, right? That just tells us the determinants are easy to compute, and we get the eigenvalues. The second one, we get a determinant of 0, and our eigenvalues are 2 and 0, and the third one we have minus 1 and minus 1. Right. So if we go back to these shapes, this now is actually telling us something, that this one, which is full quadratic, has rank 2, it has 2 eigenvalues and 2 eigenvectors. This one, which is just a pure paraboloid, right? See the shape here is flat, right? It's one axis is linear and the others are quadratic. Here, both axes have quadratic terms. This has two eigenvalues, this has one, this has two eigenvalues, but it's got negative eigenvalues. And so this allows us to look at the quadratic forms, and now, given anything, if you want to figure out is it a paraboloid, ellipsoid, or hyperboloid, you can actually just look at the signs and numbers of its eigenvalues and get where it's going. And in general, the eigenvectors will tell you the axes. Here, these were axially aligned, but they don't have to be. So if we look at our positive definite matrix that came out of this, we have V transpose A, V transpose is greater than 0. And we call this form positive definite because we're going to say V transpose A is whatever. The quadratic form is positive everywhere except for V equals 0. Okay, so if we go back to this, right, this function is positive everywhere except at the origin. And that's true for these. This one's negative everywhere, but that's negative definite. So if we go back to this example, 200.5, that quadratic leads to something for which this is true. So a positive definite symmetric matrix is a very special class matrix. We've already talked about some special properties of symmetric matrices. Now we're adding this property of positive definite. And we consider a matrix to be positive definite when it has this property. They arise in a number of very special, a number of applications. They lend themselves to, again, more efficient algorithms. And one way to sort of think about these geometrically is in a positive definite symmetric matrix, the angle between V and AV is between between minus 90 and 90. So it sort of maps things, but it doesn't map them too much in terms of where it's going to go. A is constrained in its actions, so it would, no matter what it does, if it's, if V started out in some direction, you can only sort of go plus or minus 90 degrees around V after you've applied this matrix. And you can sort of see why in many applications, if you think about how much something can bend or whatever without breaking, you just can't let it bend that much, and so you're going to have that. It just comes out of the way the matrices get defined. When you go to look at this, it's actually not sufficient to consider up here V as a unit vector. V has to be all non-zero vectors, which makes it in general very difficult to verify. There are certain matrices for which it is easy to verify, but for lots of matrices it's hard to know whether or not it's going to be positive definite. We can relate positive definite now into something that is more general. So if we suppose A is not necessarily symmetric, we can actually do something to help it become what we want. No matter what A is, A transpose A and A transpose are symmetric matrices. It's not hard to see that A transpose A, for any A, you can sit down and do the algebra, but A transpose A and A transpose are symmetric, and in fact, A transpose A and A transpose, right, are going to be positive definite. That's a little harder to see, but see they're symmetric is pretty easy. But it turns out they will always be positive definite because of the way they're defined, which we're not going to prove. But so for any matrix, when we go stick that in, you can just sort of see a little bit about this, right? We have V transpose A V, right? We're just sticking this A transpose A back into this equation. We're going to sort of verify that it's true. We get V, we collect these terms, and we notice that V transpose A transpose is just AV transpose times AV. And in general, then, we're going to call this vector Y, and this vector here Y transpose, right? We're just going to substitute variables, and we'll see that this is equal to Y transpose Y, which is greater than 0 because Y can't be orthogonal to itself, as long as this is not the 0 vector. Right? If it's a 0 vector, obviously, then it'll be equal to 0. But Y transpose Y is a distance, so it's greater than or equal to 0. These concepts and procedures, and we'll talk a lot more about when we get to chapter 16 and talk about SVD. But one of the things to get out of this is that we can turn things into symmetric forms when we need them and use them in certain ways. So even though not everything is symmetric and not everything is positive definite, we can get some related equations and use that when we go to solve equations. Oops. So looking at the determinant of a positive definite matrix, the determinant of a positive definite matrix is always positive. The matrix is always non-singular, right, because of some of these properties. So this allows us to have something where we know it's going to have a positive change in the area and it's going to be non-singular, so we can always solve it, right, because it's non-singular. And even though we've done all this for 2 by 2, this is going to applies in general to n by n matrices. There are going to be some additional requirements on the determinant as we get to higher dimensions, though. So just to sort of go through this as an example, so let's look at the quadratic form where C is the positive definite form C is equal to A transpose A. And we can now sort of think about how we're going to look at this. So think about the contour. For all these that have unit length, we can look at the question V transpose CV, and we know that's going to equal to 1. And ask what's the shape of that. This comes back to why another way of looking at why they're quadratic forms. So the contour for C1 is an ellipse of the form 2v1 squared plus 0.5 v2 squared equals 1. And if we said v1 equals 0, this will tell us that the E2 axis is the extent of the ellipse that goes from plus or minus 1 over the square root of 0.5. And if we said v2 equals 0, we get the E2 axis extents of plus or minus 1 over the square root of 2. Okay. The major axis, the longest axis here, is the E2 axis. Right? Here we're just looking at this as a matrix, finding out what is its eigenvalues and eigenvectors. The eigenvalues are 2 and 0.5, and the eigenvectors are 1, 0, 0, 1. The minor axis corresponds to the dominant eigenvector. Right? So the eigenvectors tell us the axis of the ellipse. So let's look at that. Go back and look at that graphically. Right? So here we had some general quadratic form. This tells us the axes. If we now take some general form, for this matrix, we're going to get C4 is A transpose A. That's 4, 1, 1, 1.25. You do this, stick into MATLAB now, do the eigen decomposition. Eigen decomposition in MATLAB is EYE. And we'll get that we get a rotation matrix, minus 9.95, minus 0.3, minus 0.3, and minus 0.95. That gives us R. And our eigenvectors are 0.43 and 0.92. So it's not, numbers all don't work out nicely. But this gives us an ellipse. And it's equivalent, again, remember, we rotate by R transpose, scale, and rotate back. So this tells us what it is. This matrix form tells us that the ellipse defined by 4 v1 squared, 2 v1, 1 number. And this tells us actually the directions for finding the axes of the ellipse, right? These are the lengths of the axes of the ellipse and the rotations we have to do to use that. So if we continue looking at this, the major and minor axes are not aligned with the coordinate axes. So it's not an upright ellipse, it's a rotated ellipse. So to find those major and minor axes lengths, we can use the eigen decomposition, which I just said. We go through. Now we're going to use the fact that if we're looking at this as V transpose CV, we're going to replace C with his eigen decomposition. Okay, and then we're going to get V transpose lambda times V. Why did the R's go away? Well, because V transpose and R, right, we're just going to replace those because they're just the rotations. This is going to equal to 1. That gives us lambda 1 V1 squared plus lambda 2 V1 squared is equals 1. And it gives us the equation for the quadratic. We can then get that the minor axis length is 0.48 and the major axis length is 1.4 with respect to the E1, E2 axes. So in general, if we look at repeating maps, which we talked a little bit before, eigenvalues and eigenvectors and these quadratic forms can be helpful to understand them. So if I think of my matrix A as 1.3.31, graphically I start applying it and you can sort of see it stretching things out along this direction. So this is matrix is symmetric. You can just look at it. So it's symmetric. That means it has 2 real eigenvalues and 2 orthogonal eigenvectors. And as a map, it's really repeated resulting ellipses stretched along the lambda 1 direction by 1.3 and compacted in the R2 direction by a factor of 0.7. So it's scaling along the R1 and R2 directions and has one eigenvalue greater than 1, one less than 1, which is why this direction is getting bigger and this direction is getting smaller. And these are our eigenvectors. And again, you can just stick them in, solve for them, or ask MATLAB what they are. And that gives us this property so that in general, a to the n times r1 is going to be lambda 1 to the rn power, right? So because we know that for any axis direction, all we end up doing is scaling that axis, we can sort of see that those axes keep scaling by the nth power after we do this n times, and those two directions keep scaling. So this gives you a nice way of quickly looking at what's the effect of a matrix. But this is true for symmetric matrices. If we apply it to non-symmetric matrices, so here's a general matrix. This is not symmetric. This matrix does not have real eigenvalues. If you put in lambda diagonal, do the quadratic form, it has no real eigenvalues. Nothing stays the same. So it's related to a rotation matrix in the sense that there is no direction that is fixed. But it's also can still be doing some scaling. So you'll sort of see there is a scaling going on here. But the scaling, in fact, is not always increasing. So here it's getting bigger, it's getting bigger. Now it starts getting smaller as you keep repeating this map. So for general maps, it's not as easy to think about them in terms of what their eigenvalues and eigenvectors do because they don't have real eigenvalues. You have to go to a complex plane and think slightly differently. So a bunch of terms this chapter you need to make sure you know. The fixed direction, eigenvalue, eigenvector, absolutely know what those are. Know the characteristic equation, how to derive it, write it down. Understand the dominant eigenvalue and eigenvector, thinking back to those multiple maps. If I keep applying it, the dominant one is the one that becomes bigger. How these are related to homogeneous systems, the relationship between eigenvectors and null spaces, the definition of or an orthogonal matrix, know the sort of eigenproperties of symmetric matrices, what happens when we have real eigenvalues, this idea of diagonalization of the matrix and the eigendecomposition. I wanted you to hear about the quadratic forms and where they're going and contour plots. Probably won't do a lot with those until later in the semester, but you should at least know why those are related. You sort of see some of the geometry there. Definitely understand the ideas of repeated linear maps. This is the last lecture before the midterm. The midterm will recover all the material up to Chapter 7, so even though we just covered this, go back and make sure you can relate all this material across all the